Good evening, everyone. Welcome to today's session, Lesson 1.1, What is Advanced Prompting? Imagine asking a master carpenter to build a chair. You might get a simple stool, but if you provide a detailed blueprint specifying the type of wood, the style, e.g. Queen Anne, the dimensions, and the desired finish, you get a masterpiece. Basic prompting is that simple command. Advanced prompt engineering is the detailed blueprint. It's the art of guiding an AI not just to an answer, but to the best possible answer through a well-constructed reasoning process. Now for our learning compass, learning objective. By the end of the session, you will be able to differentiate between basic prompting and advanced prompt engineering by identifying the key characteristics that define advanced techniques. For our overview of content, today we will define advanced prompt engineering, break down its core components like providing context, examples, and structure, and understand why it's necessary for solving complex tasks. For content delivery, now let's move into the core content. At its heart, a basic prompt is a direct question or command, like, "What is the capital of France?" This is perfect for retrieving simple factual information that doesn't require deep reasoning. Advanced prompt engineering, however, is a set of methods we use to improve the performance of large language models on complex tasks, tasks that require reasoning, planning, or multi-step problem solving. It is not about tricking the AI, but about guiding it with precision. So what makes a prompt advanced? Let's look at the key characteristics. First, structure and guidance. An advanced prompt provides a clear, logical structure for the AI to follow. It often guides the model through a process rather than just asking for a final answer. Second, context provisioning. It supplies the LLM with necessary background knowledge, domain-specific information, or constraints that are crucial for generating a high-quality response. Think of this as giving the AI the notes it needs before the test. Also, exemplars, few-shock prompting. It often includes high-quality examples of input-output pairs. This demonstrates the desired response format, tone, and level of detail. And lastly, decomposition. It breaks a large, complex problem down into smaller, manageable steps, which the AI can then solve sequentially. So now that we've laid the theoretical groundwork, it's time to solidify your understanding with a practical example. Consider the following task. Plan a 7-day marketing campaign for a new vegan protein bar. Prompt A. Plan a marketing campaign for my new vegan protein bar. Prompt B. Act as a senior marketing strategist. Create a detailed 7-day marketing plan for the launch of Green Fuel, a new vegan, gluten-free protein bar targeting fitness enthusiasts aged 25 to 40. The plan should include a daily theme, social media post ideas for Instagram and TikTok, and a key performance indicator, KPI, for each day. Present the output as a markdown table. Your task is to analyze Prompt B, identify and list the specific elements within it that make it an advanced prompt compared to the very basic Prompt A. Please share your analysis. I'll wait for your response.
Lesson 1.2. The Self-Consistency Principle. 1. Setting the stage. Context and relevance. Imagine a detective solving a crime. They don't just settle on the first theory that comes to mind. Instead, they generate multiple possible scenarios. The butler did it. The rival did it. It was an accident. They then examine the evidence for each path and see which one holds together most consistently. The self-consistency technique teaches an LLM to do the same thing, generate multiple reasoning paths, and then choose the most common, and therefore most likely, correct answer. 2. Our learning compass, learning objective. By the end of this lesson, you will be able to define the self-consistency technique and explain how it improves the reliability of an LLM's answers on reasoning tasks. 3. What we'll explore. Overview of content. To achieve our objective, we will define self-consistency, understand its relationship to chain-of-thought prompting, and see why taking a majority vote of several reasoning paths is more robust than relying on a single attempt. 4. Content delivery. Now, let's move into the core content. First, let's consider the problem with a single path. When using a technique like chain of thought, an LLM generates one step-by-step path to an answer. If there's a single logical error or a greedy mistake made early in that chain, the entire final answer will be wrong. It's an all-or-nothing approach. This is where self-consistency comes in. This technique enhances other prompting methods, especially chain of thought, by doing the following. Generate diverse paths. It prompts the LLM multiple times for the same problem, but with a higher temperature, which is just a setting for randomness, to generate several different chains of thought. Take a majority vote. It then analyzes the final answers from all these different paths. The answer that appears most frequently is selected as the final, most reliable output. So, why does this work? This method is effective because there are many ways to go wrong, but fewer ways to be right. A correct answer is more likely to be arrived at through multiple valid logical paths. By sampling diverse paths and finding the consensus, we marginalize or push aside the paths that contain calculation or reasoning errors. And finally, the key benefit is that self-consistency is an unsupervised technique. It requires no extra training, fine-tuning, or model changes. This makes it a powerful and easy-to-implement wrapper around existing prompting methods, and it has been shown to significantly improve accuracy on arithmetic and common-sense reasoning benchmarks. 5. Putting knowledge into practice. Interactive engagement. Now that we've laid the theoretical groundwork, it's time to solidify your understanding with a hands-on activity. Activity. Consider the following math problem. A store has 15 apples. They sell 7 and then buy 2 more boxes of 5 apples each. How many apples do they have now? Your task. Please manually create 3 different step-by-step chain of thoughts to solve this problem, following the structure below. Don't worry about getting it perfect. The goal is to see the process in action. Path 1. Start with the initial number, subtract the sold apples, calculate the new apples and add them. Path 2. Calculate the number of new apples first. Then take the initial number, subtract the sold ones, and add the new ones. Path 3. Introduce a deliberate error. Start with 15 apples, add the 2 new boxes, mistaking boxes for apples, then add the 5 apples in each box, and finally subtract the 7 sold apples. Please type out your 3 paths. I'll wait for your response.
Lesson 2.1. The Chain of Thought Revolution. 1. Setting the stage. Context and relevance. Let's start with an analogy. If you ask a student for the answer to a complex math problem and they get it wrong, you can't really help them. But if you ask them to show their work, you can pinpoint exactly where they made a mistake. Chain of thought, COT prompting does exactly this for an LLM. Instead of just asking for a final answer, it prompts the model to generate a sequence of intermediate reasoning steps, dramatically improving its performance on complex tasks. 2. Our learning compass, learning objective. By the end of this lesson, you will be able to differentiate between zero-shot and few-shot COT prompting and apply the correct technique based on the complexity of the task. 3. What we'll explore. Overview of content. Today, we will define what chain of thought is, understand why breaking down problems helps LLMs so much, and then learn the 2 primary ways to implement it. Few-shot COT, where we provide examples, and zero-shot COT, which uses a simple, almost magical phrase. 4. Content delivery. Now let's move into the core content. What is COT? Chain of thought is a prompting technique that encourages an LLM to generate a sequence of intermediate steps that lead to the final answer.
This mimics the human process of thinking through a problem step by step. Why does it work? It's effective for a few key reasons. Decomposition. It breaks a complex problem into smaller, more manageable subproblems. Resource allocation. It allows the model to dedicate more computational effort to each part of the problem rather than trying to solve it all in one go. Reduced error. It mitigates the risk of greedy decision-making where the model might commit to a wrong path early on without the chance to correct itself. Next, we'll look at the two main methods for implementing this. Method 1. Few-shot COT. Description. This involves providing the LLM with a few examples. We call these exemplars right in the prompt. Each example includes a question, a step-by-step reasoning chain, and the final answer. The model then learns this pattern and applies it to the new question you give it. Use case. This method is best for highly complex or novel tasks where the desired reasoning path is non-obvious and really needs to be demonstrated clearly. Method 2. Zero-shot COT. Description. This is a surprisingly simple yet powerful technique that works without providing any examples at all. You simply append the phrase, "Let's think step by step," to the end of your question. How it works. This simple instruction triggers the model's pre-trained ability to generate sequential reasons text. It effectively produces a chain of thought without being explicitly shown how. Use case. This is an excellent first-line approach for most reasoning tasks as it requires no effort to create examples. 5. Putting knowledge into practice. Interactive engagement. Now that we've laid the theoretical groundwork, it's time to solidify your understanding with a hands-on activity. Your task. Your goal is to solve a classic logic puzzle using both COT methods we just discussed. The puzzle. There are 3 boxes, one with apples, one with oranges, and one with a mix of both. All boxes are labeled incorrectly. You are allowed to pick only one fruit from one box to figure out the correct labels for all 3. Which box do you pick from? Your instructions. Frame a zero-shot COT prompt. Write the complete prompt you would give to an LLM. It should include the puzzle and the special phrase for zero-shot COT. Frame a few-shot COT prompt. Write a prompt that includes a different, simpler logic puzzle with its step-by-step solution already provided and then presents our main puzzle for the LLM to solve. Please share your 2 prompts. I'll be here to review them.
Lesson 2.2. Automatic COT. Auto COT. Creating high-quality examples for few-shot COT is powerful, but it's a lot of work. Imagine having to manually write detailed reasoning for dozens of problems just to get an LLM to understand a new task. It's a significant bottleneck. Automatic COT, Auto COT, solves this problem by programming the LLM to create its own examples. Our learning compass. By the end of the session, you will be able to explain the process of Auto COT and how it automates the creation of demonstrations for few-shot COT. What we'll explore. We will break down the 2-stage process of Auto COT. First, how it clusters a set of questions to find diverse samples, and second, how it uses zero-shot COT to automatically generate the reasoning chains for those samples. Content delivery. Now let's move into the core content. The main problem with what we've previously called manual COT is that crafting effective examples or demonstrations is time-consuming, requires human expertise, and is very difficult to scale across many different types of tasks. This is where Auto COT comes in as the solution. Auto COT is a framework that automatically constructs the demonstrations needed for few-shot COT. It operates in 2 main phases. Phase 1, question clustering. The process starts with a list of questions you want the LLM to solve. It converts these questions into numerical representations, or vectors, and then groups or clusters them based on their similarity. The goal here is to ensure that the examples we select are diverse and cover the different kinds of problems in your dataset. Phase 2, demonstration generation. From each of those clusters, the system selects one representative question. It then uses zero-shot COT, our let's think step-by-step technique, on this representative question to generate a reasoning chain automatically. These automatically generated question and reasoning pairs become the exemplars for a standard few-shot COT prompt. So, why does this work so well? Auto-COT brilliantly combines the simplicity of zero-shot COT with the power of few-shot COT. It uses the easy, no-human-effort method to create the materials for the powerful, example-driven method. This removes the human bottleneck and creates task-adaptive demonstrations on the fly. Putting knowledge into practice. Interactive engagement. Now that we've laid the theoretical groundwork, it's time to solidify your understanding with the short activity. Imagine you have a dataset of 100 math word problems. Some are about addition, some are about calculating percentages, and some involve speed-distance formulas. Your task. Describe in plain language how you would apply the auto-COT process to this dataset. What happens in the clustering stage? What happens in the generation stage? What is the final output you would use in your prompt? Please share your thoughts.
Lesson 2.3, Tree of Thoughts, TOT. Setting the stage, context and relevance. Let's start with an analogy. Imagine chain of thought, COT, is like a train on a single track. It follows one path of reasoning. If that track leads to a dead end or is the wrong route, the train is stuck. Now picture Tree of Thoughts, TOT. TOT is like having a map of the entire railway network. It allows the LLM to explore multiple reasoning paths, tracks, at once, evaluate which ones are promising, and even backtrack if a path proves to be a dead end. It's a much more powerful way to navigate complex problems. Our learning compass, learning objective. Our goal today is to analyze how the Tree of Thoughts framework improves upon COT by enabling exploration, evaluation, and backtracking in problem solving. What we'll explore. Overview of content. To achieve our objective, we will define the TOT framework and its key operations, thought generation, state evaluation, and search algorithms like breadth-first search. We'll see how this allows an LLM to perform deliberate planning and solve problems that require significant foresight or exploration. Content delivery. Now let's move into the core content. First, we must understand the limitation of COT. As we discussed, COT is a linear, sequential process. It's powerful, but it can't explore different possibilities in parallel or backtrack from a mistake. If it makes a wrong turn early on, the entire reasoning chain can be flawed. This is where the Tree of Thoughts comes in. TOT generalizes COT by organizing thoughts as a tree. Nodes. Think of each node in the tree as a thought, a coherent unit of text that is an intermediate step in solving a problem. Edges. Each edge represents a modification or the next logical step from the previous thought. The TOT process unfolds in 4 key steps. Decomposition. Just like COT, the problem is broken down into a number of intermediate steps. Thought generation. Here's the magic. At each step, instead of generating just one next thought, or reasoning path, the LLM generates multiple potential next thoughts or reasoning paths. This creates the branches of our tree. State evaluation. A deliberate reasoning process evaluates the progress of each path or branch. This can be done by the LLM itself, self-evaluation, or with programmed rules. It assesses whether a path is promising, a dead end, or has already solved the problem. Search. Finally, the framework uses a search algorithm, like breadth-first or depth-first search, to decide which promising branch to explore next. This is what it allows it to look ahead and backtrack from dead ends. The key advantage is clear.
TOT excels at tasks requiring planning or exploration of many possibilities, such as the game of 24 or creative writing, where a single linear path is highly unlikely to succeed. V. Putting knowledge into practice, interactive engagement. Now that we've laid the theoretical groundwork, it's time to solidify your understanding with a hands-on activity. Let's apply TOT to the game of 24. The goal is to use the numbers 4, 9, 10, 10, and basic arithmetic, plus, minus, times, divide, to reach the number 24. Your task, instead of trying to solve it directly, just sketch out the beginning of a tree of thoughts for this problem. Think about generating a few different starting paths. For example, root the numbers 4, 9, 10, 10. Level 1, the first step. What are 2 or 3 different first steps you could take? Don't worry about solving it yet, just create the first branches of the tree. I'll wait for your response.
Lesson 3.1. Reason and Act. ReAct. I. Setting the stage. Context and relevance. Imagine a brilliant detective locked in a room. They can make incredible deductions, but they can't check a new fact, look up a license plate, or visit a crime scene. Their reasoning is limited by their initial knowledge. The ReAct framework is like giving that detective a phone and an internet connection. It allows an LLM to interleave its internal reasoning with external actions, like searching the web or querying a database. I. Our learning compass. Learning objective. By the end of this session, you will be able to deconstruct a ReAct prompt into its core components, thought, action, and observation, and explain how they work together to solve a problem. 3. What we'll explore. Overview of content. Today we will define the ReAct framework and see how it enables an LLM to dynamically interact with external tools to gather information, overcoming critical issues like hallucination and outdated knowledge. IV. Content delivery. Now let's move into the core content of ReAct. The core idea of ReAct is to combine reasoning, similar to what we saw in Chain of Thought, and acting, using external tools, in an interleaved loop. This creates a powerful synergy where the model can think about what it needs to know, go get that information, and then think about the new information to decide on the next step. This process works as a cycle of 3 key components. Thought. The LLM analyzes the problem and generates a private, step-by-step reasoning trace about what it should do next. For example, I need to find the current Prime Minister of the UK. I should use a search tool. Action. Based on that thought, the LLM formulates a command to an external tool. For example, action, search, the current Prime Minister of the UK. Observation. The system executes the action and returns the result back to the LLM. For example, observation, search results showing the current Prime Minister is Keir Starmer as of July 2024. This cycle then repeats. The LLM receives the observation, generates a new thought. Example, okay, I have the name. Now the user wants to know his political party. I should search for that. Takes a new action, and so on until it has gathered enough information to formulate the final answer. The key benefits of this approach are significant. Reduces hallucination by verifying facts with external tools. It provides up-to-date information. It can access information created long after its training cutoff date. Interpretability. The thought process is explicit, so we as humans can see why the agent took a certain action, which is fantastic for debugging and trust. V. Putting knowledge into practice. Interactive engagement. Now that we've laid the theoretical groundwork, it's time to solidify your understanding with a short activity. Your task is to answer the question, what was the box office revenue for the highest-grossing movie directed by the person who directed Oppenheimer? Below are the first 2 steps an LLM using ReAct would take. Your job is to write out step 3, including the thought, action, and observation. Step 1. Thought. I first need to find who directed Oppenheimer. I will use search. Action, search, director of Oppenheimer. Observation, Christopher Nolan. Step 2. Thought. Now I know the director is Christopher Nolan. I need to find his highest grossing movie. I will use search. Action, search, highest grossing movie directed by Christopher Nolan. Observation, The Dark Knight. Step 3. Thought. Action, observation. Please provide your answer for Step 3.
Lesson 3.2, Reasoning without observation, or ReWu. Setting the stage, context and relevance. The ReAct framework we've studied is powerful, but it can be slow and expensive. It uses a massive, powerful LLM for every single step, planning, deciding which tool to use, and summarizing the final answer. Imagine building a house this way. It's like having your master architect not only draw the blueprints, but also lay every single brick, run every wire, and paint every wall. It's thorough, but incredibly inefficient. ReWu is an efficiency-focused redesign of this process. It's like having a project team, a planner, the architect, who creates a detailed blueprint, skilled workers, the electricians, plumbers, and carpenters, who execute specific tasks using their tools, and a final solver, who's the site foreman, who inspects all the finished work and confirms the house is complete. This system decouples the steps to make the entire process much more efficient. Our learning compass, learning objective. Our goal today is to differentiate between the ReAct and ReWu architectures by explaining the roles of the planner, worker, and solver modules in ReWu. What we'll explore: overview of content. To achieve our objective, we will explore the ReWu framework, which separates the reasoning and tool use process into 3 distinct modules to improve token efficiency, speed, and even allow for offloading tasks to smaller, specialized models. Now, let's move into the core content. First, let's remember the inefficiency of ReAct. In ReAct, a large and expensive LLM is invoked repeatedly for the entire thought-action-observation loop. This consumes a huge number of tokens, with all the intermediate reasoning steps making it costly and slow. To solve this, ReWu introduces a new architecture that divides the workflow into 3 specialized modules. The planner, this is a powerful LLM that receives the user's question and creates a complete step-by-step plan up front. It outlines all the tool calls that will be needed and how the output of one step will become the input for the next. For example, it might generate a plan like #E1 equals search, #E2 equals calculator, #E1. Crucially, the planner does not execute the plan. It only creates it. The worker, this module takes the complete plan from the planner and executes all the tool calls. For each step, it calls the specified tool, like a search API or a calculator, and retrieves the evidence. The worker can even be a smaller, cheaper model or just a simple non-AI function, which is a major source of savings. The solver, this is another powerful LLM. It receives the original question, the plan from the planner, and all the evidence gathered by the worker. Its one and only job is to synthesize all this information into a final human-readable answer. This brings us to the key advantage: efficiency. ReWu significantly reduces the number of tokens sent to the expensive, large LLM. The planner creates one plan, the workers execute it, often using cheaper systems, and the solver synthesizes the results once. This is much cheaper and faster than the iterative loop of ReAct and opens the door for parallel processing and offloading work to smaller models. Putting knowledge into practice. Interactive engagement. Now that we've laid the theoretical groundwork, it's time to solidify your understanding with a practical example. Let's use the same question from our ReAct lesson. What was the box office revenue for the highest-grossing movie directed by the person who directed Oppenheimer? Your task: based on what we just learned, describe the likely output of each ReWu module for this problem. What would the planner produce? What evidence would the worker gather? And what would the solver say? Please take a moment to write out your thoughts on the planner, worker, and solver outputs. I'll wait for your response.
Lesson 3.3, Automatic Reasoning and Tool Use, ART. 1. Setting the stage, context, and relevance. We've learned how to use tools for a specific task, but what if we want our AI to be able to solve a brand new type of problem it has never seen before?
Do we have to manually write a new ReAct or ReWoo prompt every time? ART is a framework that automates this. It's like giving an AI a library of solved problems and a toolbox and letting it learn how to combine them to tackle a new challenge on its own. 2. Our learning compass, learning objective. By the end of this lesson, you will be able to explain how ART automates problem solving for new tasks by selecting and composing examples from a task and tool library. 3. What we'll explore. Overview of content. We will learn how ART leverages a library of existing solutions to automatically generate a multi-step plan, a decomposition for a new, unseen task. It then executes this plan, calling tools as needed, demonstrating a powerful form of few-shot learning for complex procedures. 4. Content delivery. Now let's move into the core content. The primary goal of ART is to enable an LLM to solve a new task with few-shot prompting, even when the task requires multi-step reasoning and tool use without needing a human to manually craft the examples. The ART framework accomplishes this in 4 key steps. Task and tool library. First, ART maintains a library of solved problems. Each entry in this library contains a task decomposition, a high-level plan that shows the reasoning steps and the specific tools used to solve that problem. Demonstration selection. When a new task comes in, ART searches its task library to find the most relevant solved examples. Think of it like a librarian finding the best how-to guides for your specific project. Plan generation. Next, the LLM is prompted with these selected examples and the new task. It learns the pattern from the examples and generates a new decomposition, a step-by-step plan for the new task. This plan will include placeholders for the tool calls it needs to make. Plan execution. Finally, ART executes the generated plan. It proceeds with LLM generation for reasoning steps and pauses whenever a tool needs to be called. It calls the tool, gets the output, and seamlessly integrates it back into the generation process to complete the next step. A key feature of ART is the option for a human in the loop. A human can edit the generated plans or add new, corrected solutions to the task library, allowing the system to learn and improve over time. 5. Putting knowledge into practice. Interactive engagement. Now that we've laid the theoretical groundwork, it's time to solidify your understanding. Imagine your task library contains 2 solved problems. Example 1. Fact-checking. A plan that shows how to use search bracket to verify 2 separate claims and then use the LLM to compare them. Example 2. Calculation. A plan that shows how to extract numbers from text and use calculator bracket to find their sum. Your new task is fact-check the populations of California and Texas and calculate the difference between them. Based on what you've learned, describe how ART would likely generate a plan for this new task. What would the decomposition look like? Please share your thoughts, and then we'll review it together.
Lesson 4.1. The Reflection Framework. When humans fail at a task, we don't just try the exact same thing again. We stop, think about why we failed, and create a new strategy. The reflection framework gives this critical ability to AI agents. It's a method for teaching an agent to perform self-reflection on its failures, store that learning as a memory, and use it to make better decisions in the future. Our learning compass, learning objective. By the end of this lesson, you will be able to describe the reflection agent's process of using linguistic feedback and self-reflection to improve performance on subsequent trials. Our previous tutorials. We have previously covered the ReAct framework, which allows an agent to interact with an environment, and the memory framework, which provides a mechanism for agents to store information over time. These techniques come earlier in the series and are lessons from 3.4, 4.3, and 4.7, respectively. What we'll explore. Overview of content.
Today, we will define the reflection framework, see how it uses a memory buffer to store learnings from trial and error, and understand how this process of self-correction leads to significant performance improvements in reasoning, decision-making, and even coding tasks. Content delivery. Now, let's move into the core content. The fundamental problem that reflection solves is that standard AI agents are often stateless. This means if they fail at a task, they will make the exact same mistake again on the next try unless a human intervenes to rewrite their prompt. They don't learn from experience. The reflection framework changes this by equipping an agent with a mechanism to learn from its past failures. The process works like this. Trial. The agent attempts a task like trying to solve a programming challenge. Feedback. The agent receives a feedback signal. This can be a simple pass-fail, but more powerfully, it can be linguistic feedback, like a compiler error message from a program. Self-reflection. This is the key step. The agent is prompted to reflect on the failure. It generates a short, natural language summary of what went wrong and what a potential strategy to avoid this failure in the future might be. Memory storage. This self-generated reflection is then stored in what's called an episodic memory buffer. Next trial. On the next attempt, the agent is prompted with not only the original goal, but also with its own self-reflections from past failures. This additional context guides the agent to make a better decision and avoid repeating mistakes. The framework is particularly powerful when it can convert simple feedback like an error code into a rich, verbal self-reflection. This provides much more useful information for the next trial than a simple fail signal and has led to state-of-the-art results in complex tasks like program synthesis. Interactive engagement. Now that we've laid the theoretical groundwork, it's time to solidify your understanding with an activity. Imagine an AI agent is tasked with writing a Python function to read the first line of a file. Trial 1, the agent generates code that tries to open a file that doesn't exist. Feedback, the Python interpreter returns a file not found error. Your task, write a plausible self-reflection that the reflection agent might generate after this failure. How would this reflection help in Trial 2? I will wait for your response.
Lesson 4.2 Automated Prompt Design, APE, and Expert Prompting. We've spent this whole course learning how to craft better prompts. But what if we could use an LLM to do this work for us? Automatic Prompt Engineering, APE, is a technique that does just that. It treats the prompt itself as a problem to be optimized. A particularly effective strategy that has emerged is expert prompting, where we automatically generate a detailed expert persona for the LLM to adopt. Now, let's look at our learning compass. Our objective today is to explain the goal of automatic prompt engineering, APE, and describe how the expert prompting strategy works. Now, what we'll explore? We will cover two related concepts. First, we'll understand the APE process of using an LLM to generate and score candidate prompts to find the best one. Second, we'll dive into expert prompting, a powerful and easily automated technique for creating highly effective, specialized prompts. Now, let's move into the core content. Automatic prompt engineering. The goal is to automate the discovery of the most effective instruction or prompt for a given task. The process? It follows a simple three-step cycle. Candidate generation. An LLM is used to generate a large pool of potential instruction prompts for a task. Scoring. Each candidate prompt is tested on a set of problems. A score function, like accuracy, measures how well the prompt performs. Selection. The highest scoring prompt is selected as the optimal instruction. The famous example, this very process was used to improve upon the well-known prompt, "Let's think step by step." APE discovered the even more effective prompt, "Let's work this out in a step-by-step way to be sure we have the right answer." Next, we'll look at a specific, powerful APE strategy, expert prompting. The strategy is this is a simple but highly effective method where the prompt instructs the LLM to act as a distinguished expert tailored to the specific task. Key elements: instead of a generic instruction, you define a detailed persona. Let's compare. Poor, write about the benefits of intermittent fasting. Good, expert prompt, you are a world-renowned nutritional scientist and PhD with 20 years of experience specializing in metabolic health and intermittent fasting. Your task is to write a comprehensive overview of the benefits of intermittent fasting, citing key scientific studies and explaining the biological mechanisms involved in a clear, accessible manner. Automation: the best part is that these expert identities can be automatically generated using an LLM, making this a practical and scalable strategy. Now, putting knowledge into practice, now that you've laid the theoretical groundwork, it's time to solidify your understanding with a practical exercise. Imagine you need to generate a legal analysis of a sample contract to identify potential risks. Your task: write a simple, non-expert prompt for this task. Write a detailed expert prompt for the same task. Be specific about the expert's qualifications, experience, and what they should focus on. Take your time to craft both prompts, and I'll be right here to review them.
Lesson 4.3: Practical Tools for Prompt Engineering. We've learned the theory behind many advanced prompting techniques like ReAct, self-consistency, and chaining. But how do we implement them in a real application without writing thousands of lines of code from scratch? This is where developer tools and frameworks come in. Think of them as a professional chef's toolkit. A chef could forge their own knives and build their own oven, but it's far more effective to use high-quality, pre-made tools to create a masterpiece. These frameworks provide the building blocks to bring powerful AI concepts to life quickly and reliably. Our Learning Compass Learning Objective. By the end of this session, you will be able to identify at least 3 common prompt engineering tools and describe the primary problem each one is designed to solve. What we'll explore: overview of content. We will survey 4 of the most influential tools in the prompt engineering space: LangChain, Semantic Kernel, Guidance, and AutoGPT. We will focus on understanding their core purpose and how they help developers build sophisticated LLM-powered applications. Content delivery. Now let's move into the core content. We'll examine each tool one by one. 1. LangChain. Core purpose. LangChain is a versatile framework for chaining LLM calls together and integrating them with external tools and data. It is the go-to tool for building agentic applications. What it solves: it provides pre-built components for nearly everything we've discussed. If you want to implement a ReAct agent that can search the web and do calculations, LangChain has modules for that. It dramatically simplifies connecting LLMs to APIs, databases, and document stores. 2. Semantic Kernel. Core purpose. This is an open-source SDK from Microsoft designed to easily integrate LLMs into conventional enterprise applications, e.g. written in C# or Python. What it solves: it excels at bridging the gap between natural language prompts, which it calls semantic functions, and traditional code, native functions. Its key feature is a planner that can automatically create a workflow combining these functions to fulfill a user's request, making it ideal for adding AI brains to existing software. 3. Guidance AI. Core purpose. Guidance is a templating language for gaining fine-grained control over the LLM's output generation. What it solves: standard prompting can feel like a black box. Guidance allows you to interleave generation with strict controls, conditionals, and loops directly within the prompt template. This ensures the output conforms to a specific structure, like valid JSON, and is more efficient by constraining the model's choices. 4. AutoGPT. Core purpose. AutoGPT is an experimental open-source application that demonstrates a fully autonomous AI agent. What it solves as a concept:
While more of a showcase than a developer framework, AutoGPT was one of the first viral examples of an agent that could take a high-level goal, break it down into subtasks, and use tools like web search and file I/O to pursue the goal without continuous human input. It demonstrates how techniques like memory management and prompt chaining can be combined to create autonomous systems. Putting knowledge into practice, interactive engagement. Now that we've laid the theoretical groundwork, it's time to solidify your understanding with a short activity. You are an application developer with a specific need. For each scenario below, tell me which tool we discussed would be the most appropriate choice. Scenario 1. You need to build a chatbot that can answer questions about your company's internal documents. The chatbot must search the documents, synthesize answers, and remember past conversations. Scenario 2. You want to ensure an LLM always outputs a user's profile in a perfectly formatted JSON object with no extra conversational text. Scenario 3. You want to add a feature to your existing C# e-commerce application that allows users to ask, "Find me a blue dress under $50 with good reviews," and have it automatically apply the right filters. Take your time and let me know your choices for all three scenarios.
Course conclusion. Review of the Master Course on Advanced Prompt Engineering. You have now completed the Master Course on Advanced Prompt Engineering. Across 4 incredible modules, you have journeyed from writing simple instructions to architecting complex autonomous AI systems. You have progressed from a basic prompter to an instructional architect, capable of guiding large language models to solve problems with precision, reason, and creativity. Our learning compass, learning objective. Our objective today is simple but powerful: to review and consolidate the critical skills you have acquired throughout this entire master course. What we'll explore: overview of content. To achieve this, we will briefly revisit the key concepts from each of our 4 modules. Module 1, Foundations and Self-Consistency. Module 2, Chain of Thought and Tree of Thoughts. Module 3, Tool Integration with ReAct, ReWoo, and ART. Module 4, Autonomous Frameworks and Developer Tools. Content Delivery. Now let's move into the core content and celebrate the knowledge you've built. Let's briefly review the critical skills you have acquired. In Module 1, you established the foundations, learning to differentiate between basic and advanced prompts, and mastering the self-consistency principle to ensure your answers are robust and reliable. In Module 2, you dove into the chain of thought revolution, learning to prompt models to show their work with both zero-shot and few-shot code. You then evolved this concept into the more powerful tree of thoughts, enabling models to explore, evaluate, and backtrack through complex problem spaces. Next, in Module 3, you broke the model out of its black box by integrating external tools. You learned the ReAct and ReWoo frameworks to allow agents to interact with the world, gathering real-time data to overcome hallucination and outdated knowledge. You also saw how ART can automate the creation of these complex plans for new tasks. Finally, in Module 4, you explored the frontier of autonomous frameworks and strategies. You learned how to build agents that learn from their mistakes with reflection, design their own expert personas with APE and expert prompting, and you surveyed the critical developer tools like LangChain and Semantic Kernel that bring these theories to life. Putting knowledge into practice, interactive engagement. Now that we've laid the theoretical groundwork of our review, it's time to solidify your understanding with a moment of personal reflection. Activity. Reflect on the entire course. Which single technique or framework, like chain of thought, ReAct, reflection, or another, do you believe will be most impactful in your own work or projects, and why? Please take a moment to share your thoughts.